Michael, today you and I are going to make a volcano.
I've made one of those before.
Yeah?
Yeah, I made it out of paper mache.
Well, this one's made out of asbestos paper. And if I put the fuse in the top, I think maybe you'll get the idea why.
Oh.
Because this one's going to be fire. What did you make yours out of?
Well, I made mine out of baking soda and vinegar. Mm-hmm. And when I put them together, it started erupting, and it made a bunch of bubbles come out.
Did you add soap?
No.
That's a good idea. Add either liquid or powdered soap, because then it actually flows down, you know, like a whole bunch of foam. This time, we are going to actually make it with fire. So if you pay attention and want to try to repeat this, well, you better be sure that your teacher or your parents are around.
I see.
You notice I've covered the table with a piece of plywood. That ought to give you a clue that we're really going to have fireworks. Here's what I power mine with.
Ammonium dichromate.
Yeah, ammonium dichromate. And the dichromate on the end says that there's oxygen inside here. So when we put the chemical inside there and light it, the thing is going to keep on going. We don't have to add any oxygen at all. Here, you put in a teaspoon in the bottom.
Okay.
So you have a can inside so that you can put the ammonium dichromate all the way down in the bottom. See, it's a yellow or orange sort of powder. Okay, now I'll add a little of this.
What is it?
Well, these are sparklers broken up.
Oh, I call them sparklies.
Sparklies? Okay.
Yeah.
Same thing. Okay, a little more. Okay, a little more sparklies.
Why is this orange?
Well, that's the color of the chemical until it burns. And when it starts burning, you'll see it'll change color. Do you know what kind of a volcano we're making, by the way?
No.
What's the shape?
Well, it looks like a cone.
Yes, and it's called a cinder cone because it's cone shaped. Go ahead, put some more in. And the cone is made by cinders coming out of the volcano, building up the cone. Then there are other types, too. The kind you made is more like a lava type, right?
Yeah.
Okay, one nice big heaping teaspoon to finish it. Okay. And a few little sparklies, you call them?
Yeah.
Okay.
Sparklies.
Sparklies. Okay, let's move everything out of the way. This is the kind of volcano where you don't have to worry about the seismologist giving you a warning.
Yeah.
Because we can see when it's going to go by the fuse, right?
Yeah.
Okay, ready to light it?
Yep.
Okay, stand back. I'll turn out the lights first. And then you go ahead and light it. Go ahead. Just put it there on that old plywood. Okay.
That looks neat.
Yeah. Clear the decks because here comes a volcanic eruption. There we go. Gee, here's a plastic bottle that liquid soap comes in. And right up there, floating at the top, is a medicine dropper that looks like an ordinary medicine dropper, but is not. It instead is a magic medicine dropper because on command, down.
It's going down.
And on command, up.
It's going up.
Now I can make it stop right there. Down, magic medicine dropper, and stop.
How did you do that?
What do you mean? It's a magic medicine dropper.
Come on, how'd you do that?
You mean all magic tricks have tricks? So there's a trick about doing this. See the water inside the medicine dropper?
Yeah.
I'm going to squeeze on it. Watch what happens to it.
Water goes up and down.
Yes. That give you a clue as to why the dropper goes up and down?
Yeah.
When I squeeze on it, what happens?
The water goes up.
Yeah. Think of the little dropper in there as a whole unit made of glass, rubber on the top, has water in it and air. And the whole combination is slightly heavier or lighter than an equal amount of water, and that's why it floats. Now, if we can add some weight to it, like some water,
It'll sink.
we make it a little heavier. And that's what you do by squeezing. See it?
Yeah.
Add just enough weight to make the whole system heavier, and down it goes. And then when you let go of the pressure, some of the water is squeezed back out again, and it goes up. You try.
Okay.
First of all, make it go down. Crunch. Now that's working well because you're squeezing hard. Now make it stop right there. Okay. Squeeze it to get it starting down.
Okay, it's going down.
All right, a little more. Stop. Very good. If you want to make one of these at home now, get a bottle like this that's liquid soap comes in. Fill it to the very top with water. Take a medicine dropper and in another glass or a pitcher like this, squeeze just enough water in it so it just barely floats. Put it inside here, put the top on, and you're all set to make a magic medicine dropper.
I have something like this at home, Mr. Wizard.
You do?
Yep. It's like a Christmas tree. And it has a little plate on the bottom. There's 2 candles. And the hot air, it rises. And there's this little kind of a vent thing on top. And it makes it go around and it hits little bells.
Right. That's a very popular sort of thing you get out at Christmas time. Well, here's a sort of simple version you can make at home out of a piece of paper. But there's one other important part of it that I think you ought to realize. First of all, come on over here. You can see what you do is you get a piece of paper and you cut it into a spiral.
Oh, yeah.
You see, you just cut around here until it gets down to until there's about that much in the center. Then here is the other very important part. You recognize that?
Yeah.
A metal thimble. Plastic works pretty well, but metal is better. Now come on over here, I'll show you. You think you can put the rest of it together?
Yeah, that looks like, see, this is the spool, and you stick it on the lamp, and in the spool you stick a pencil, and in the eraser of the pencil you stick an upside-down needle.
Right. That's very important because watch what happens when I put the thimble on top of the needle and give it a spin.
How come it's not stopping?
Yes. That's a very important pivot for home scientists. They've been using the needle and the thimble for years as a pivot because it takes, because there's such a sharp point on the needle and the metal thimble, there's very little contact between the two because the point is so sharp. So it takes very little energy to make it go around. And that's extremely important because the force that makes this piece of paper twirl is very, very low. And there it goes. Where does the energy come from to make this thing go now?
Hot air is pushing up on it.
Well, yes, that's true. Most people say that. Hot air is pushing up or hot air rises. But it seems strange, doesn't it, that gravity pulls everything else down. Why doesn't it pull down on hot air?
It's light?
It's light. Well, that's part of the explanation. Think of it this way. As you know, when you heat up air, it expands. So an equal amount of hot air weighs less than an equal amount of cold air. So gravity pulling down on the cold air, in effect, flows and forces the hot air up. So hot air doesn't rise, it's pushed up by cold air. And that's what's making this thing. So when somebody asks you, why is this thing going around? It's true, it's because of the hot air going up, but you can be very smart and say it's also because of what?
Gravity.
Right.
Calories per day.
Right. There are the requirements for children of various ages. But before we take a look at them, I'd have to make sure that you know what a calorie is. What's a calorie?
I think it's body heat.
Pretty close, yes. Calories are units of heat. It can be heat that came from any place, inside your body, from coal or fire or any kind. That's calorie. That means heat. And here are the number of calories that you need every day to get from your food. Where do you fit?
Well, I'm 12, so I'd fit right here.
Yeah.
So I'd need 1,800 to 2,400 calories per day.
Right. Now, what happens to those calories when you eat them?
You store them for energy?
Yes, you use them for energy. If you eat too many of them, you store them as fat. That's why people count calories. Then you're also, you're warm, right?
Right.
You have a temperature.
Yes.
Right. And so the calories are used to do that. But you lose a lot of them every day. So we're going to look at what happens to the heat that's given off by your body. And I don't know, have you had this yet? Various methods of getting heat from one place to the other?
Not yet.
Okay, well, here's a hot iron, so be careful.
Okay.
We can use it to illustrate most of the ways that heat gets from one place to the other. First, conduction. If you took your finger and you touched the iron, which you don't want to because it's
Right.
hot, if you touched it, the heat would be transferred from the steel plate of the iron over to your finger. That's conduction.
Okay.
Next, convection. The iron is heating up the air over here, so you take your hand and put it up here. Feel the heat?
Yes, it's warm.
Okay. The air is flowing up there and heating up your hand. That's convection. Next, evaporation. Hold out your hand. Here is some rubbing alcohol.
Oh, that's cold.
Yeah, doesn't it feel cool?
Yes.
Yeah. Now, the reason why it feels cool, it's taking heat from your body. You see, in order for the little alcohol molecule to evaporate, which means jump off into the air and go away, right? That's what evaporation is. It has to get heat from someplace. So it's taking it from your skin. That's why it feels cold. The same thing happens when you perspire. Perspiration comes out here and evaporates, and that's what makes you cool. So that's the third method. What's the last one?
Radiation.
Now take your hand and put it by the iron, but don't touch it, and just keep moving it closer and closer until you can feel the heat.
Right there.
Right there. Now, invisible rays are coming from the iron. When they hit your hand, they're changed to heat.
Oh.
And that's radiation. Okay. So there are the four methods how you get rid of heat every day. Let's move this iron out of the way because it's hot and I don't want to get you. Now, what I'd like you to do is to make an educated guess as to what the percentages are of how you lose heat. I have the correct answers over there under these little yellow pieces of paper, and I want to have you write your guess over here.
Okay.
If each one were 25%, you'd end up with 100, right?
Right.
So you go ahead. Here's a pen, and you write your best guess as to the various ways you lose heat.
Conduction that's when heat travels from one thing directly to
Touching,
another.
right.
Okay. So I'd say about 30.
Okay. Let me get over a little closer so you don't have to lean over so far.
Okay.
That's 30. What's next?
Convection. That's when the heat heats up the air. So I'd say 25.
Okay.
So I have 55 left. Evaporation.
We have 45 left. Careful.
Oh, 45 left.
Yes.
I'd say bigger margin, like 35.
Wow.
And radiation, 10.
Okay. Now we will see how close you are to being right. Because under here are the correct answers.
3%?
Yes. Isn't that surprising?
Yes.
Well, not really, when you realize that about the only thing you're heating up by conduction is your clothing.
Oh.
Right?
Yes.
Okay.
12%?
12% by convection. After all, when you have your clothes on, the air can't flow next to your body very easily.
Oh.
So that's one of the reasons why you wear clothes, to keep that convection from carrying away the heat. So that was 12.
Well, I'm closer here.
Evaporation. You're closer, you were a little high, but 25% after all, the only time that really makes a big difference is when you perspire and you're actually having something that can evaporate. So you can almost tell by making some calculations what this one's going to be, right?
60%.
Yes, 60%. Now, doesn't that seem amazing?
Yes.
In fact, it's been estimated that a normal adult gives off about as much heat as a 100-watt light bulb, and you know how much heat that is.
Yes.
It's all radiation. In fact, there's an old saying, if you want to keep your feet warm on a cold winter day, wear a hat. You see why?
Yes.
Because your head is radiating a lot of heat. So those are the various ways that you lose body heat. Warren, would you please fold that paper in half for me? Now again, fold it in half again. Okay, keep going.
Do you want me to fold this 8 times?
Oh, you know this trick.
Yep.
Where did you hear about this?
On the radio.
Okay. Did you try folding it?
Yeah.
How many times did you fold it?
8 times.
How are you doing there?
4.
4. 5, 6. How come you could do it with 8?
I tried a bigger piece of newspaper.
Like this?
Yeah.
Okay, that's what I was going to have you try next. Go ahead and try counting this one now.
Okay.
Keep track of them now. This one you said you could fold 8 times?
1,
2,
2,
3,
3, 4, 5, 6, 7, 8.
You count that as a fold?
It's in half.
How about a bigger piece yet?
I don't know. It might not work.
All right. Let's try it first. Here's a piece of adding machine tape. So take it and go way back over there on the other side of the room. We'll pull off a nice long piece. Okay, come on, bring it over to me and start folding. Now we have 1,
2, 3, 4, 5,
okay, you can handle it from there on.
6, 7.
7.
Can't get it anymore.
Yeah, so, in fact, the longer sheet wasn't even as easy to fold. Now, why is that?
Because the thickness of the paper is always the same.
Always roughly the same,
Yeah.
yes. But the other thing that's kind of interesting about that kind of a trick, that you can't fold a paper any more than 8 times, is the fact that when you double something, it gets a big number very quickly. In fact, here's an adding machine. Multiply 2 8 times. That will be each fold, right? The first one, 2, that's number 1.
That's number 2, 3, 4, 5, 6, 7, 8.
What's the number?
256.
256 sheets you're trying to... You've bought a ream of paper. How many sheets?
Half of it.
Yeah, half. In other words, there's 500 sheets in a ream, and you were trying to fold half a ream. Impossible. So that's all right. Go ahead and challenge your friends. Regardless of the size of the paper, they won't be able to fold it any more than 8 times. Here's a frontier in imagery. This is an outline of a supersonic airplane, but not a real one. It's a mathematical model of a plane that was fed into a computer along with the calculated stresses on the surfaces indicated by the various colors. With the computer controls, the model can be rotated and flexed to see what happens to the stress. The changing colors give the designers of the plane an indication of how it should be engineered to withstand the forces encountered when it's flying faster than the speed of sound. Graduate students prepared the mathematical model and fed it into the computer as part of their work in the Computer Engineering and Science Department at the Case Institute of Technology in Cleveland, Ohio. Experimenting with a model made up of numbers, which become images that can be manipulated and studied on a computer screen, combines mathematics and engineering in a new frontier. Lila, you know the dimensions of this piece of paper.
Yeah.
What are they?
11 by 8.5.
Okay. What I want you to do now is to cut a hole big enough for you to walk through in this piece of paper.
You can't do that. That's impossible. Cutting a hole in this piece of paper?
Mm-hmm.
You can't do that.
Okay, before you leave today, I think we will have a hole in a piece of paper this big enough for you to jump through.
Jump through?
Yes.
No way.
All right. First of all, just cut the biggest hole you can in this piece of paper.
Okay.
That's as big as you can make it?
Well, except for the corners.
Yeah, you could make it just a little bit bigger. Not certainly big enough for you to jump through.
No.
Okay, now, why do you think that you're having problem trying to solve this little puzzle? Here's why. Remember I said in the beginning, how big is this piece of paper?
Yeah.
That was to make you think of the dimensions of the paper. So that when I said you want to cut a hole big enough to jump through, your mind said, well, the dimensions of the paper are 8.5 by 11, therefore the hole can't be any bigger.
Yeah, that's right.
Not right. Not
No?
right. You have to make the hole bigger than that, obviously. Okay. That's one thing. Look at all the paper you wasted.
Well, you can't use that to make a hole.
Well, you'll have to somehow figure it out so that you can take all of the center part and make it a part of the ridge around the edge. Okay? Third thing. When I said hole, did you think of something sort of round? You could have cut something kind of round.
Round.
Okay, but a buttonhole is a hole. How would you describe a buttonhole?
Slit.
A slit. Okay. So that's what you have to do. Get your mind thinking away from this dimension of the paper. Okay. Somehow get all of the paper as part of the edge around the hole and cut a series of slits. And here's what you do. Each of these black lines is a cut, including that one down there at the fold. See, that's where I folded the paper like that. Put your finger down here and trace what happens.
It's one continuous line.
Yes. And if you cut both sides out at once, you're going to have one continuous line all the way around.
Yeah.
So that's what you do. Okay, cut a series of slits. Take the scissors and first cut like that. Okay. Now cut the other side over here. Try not to cut my finger, please. Now cut the fold. Okay, now, see these two lines here?
Yeah.
Okay, cut those. Okay. I'll turn the paper around. You cut 3 more. 1, 2, 3.
Sorry.
Okay, now open it up.
That's a big hole.
Yes, certainly big enough to put around you,
Yeah.
but not big enough to jump through. Here, you want to pick it up, please? See, what you have to do, Lala, when you want to make a hole big enough to jump through, is the same idea as that you just now, cut it into a series of slits like that, but make the spaces between the slits smaller. Very, very small. The smaller you make them, the bigger the hole. In fact, here, look. I have one that I cut out exactly like you did, but I made the slits that close together. And watch the size of this hole. Would you come with me, please? Stand out there, turn around. I have put a couple of tacks on the door, and I can put one side over there, one side over here. Are you ready? Jump through my piece of paper.